Right now, these review materials for the exam, they're available in Moodle, of course, so you can have a look at those. All right, now remember that we're going back to to just after the first exam. So the first thing that we did there was couples, which are kind of a pure moment with no associated force. Couples have the same magnitude anywhere on the object. So if you look at the units on couples, they're Newton meters or pound feet or something like that. You don't have to consider the moment arm from a point to a couple because the moment arm is already in the couple. If you look at the units, again, it's Newton meters or pound feet. So couples have the same magnitude anywhere in the object. All right, the next thing we did was distributed loads. Area of the loading diagram is the total force. You apply that force at the centroid of the load. You can cut up composite loading diagrams. The next thing was resultants, where we look at the net effect of a group of forces in couples. So we look at sum of Fx, sum of Fy, and sum of moments. The resultant force is the square root of sum of the squares of sum of Fx and sum of Fy. The angle would be the arctan of sum of Fy over sum of Fx. And then the x offset distance would be the moment divided by Fy, and the y offset distance would be the moment divided by Fx. So if you need to place the resultant force in a location such that it will cause the resultant moment, you use those two formulas down here at the bottom to get whichever kind of displacement you want, either x or y. Okay, now in past years I've seen people who didn't really study this adequately for the test. I know it's been a while back, but the homework problems we did on this are 231, 232, 241, and 242. So please have a look at those and be sure that you understand resultants and how they work. Okay, there might be a free body diagram problem on the test. What you do there is you decide what you want the body to be, draw a boundary around it, show the forces acting on the body. And then what you really want to do on these is identify the types of supports. The supports exert forces and perhaps couples to hold the object in static equilibrium. So what you do is you focus on the support and then find the motion that the support prevents, and then translate that into forces and couples. So you really want to kind of have just a focus on each individual support. So if you have a pin joint, you'll have two forces, x and y. If you have a cantilever support, you'll have two forces, x and y, plus a couple. If you have a roller or a smooth surface, you will draw the force perpendicular to the surface. Okay, so just focus on these supports, draw in the forces that represent the motions that are prevented by the supports. All right, 2D equilibrium, start with a free body diagram, then use sum of Fx, sum of Fy, and sum of moments are 0 to solve. Quite often, the first equation should be the sum of moments about a point where two of the unknowns intersect. That way you can solve for the third. Because 2D equilibrium, you have three equations, you can only solve for three unknowns. So if you can identify a point that has two of the unknowns intersecting in it, you can use that, take a moment, and solve for the third force. Okay, once you identify the point about which you might want to take moments, you want to find x and y dimensions from this point to the forces and reactions. Okay, 3D equilibrium, you've got 6 equations, the sum of force equations and the sum of moment equations. All right, now there's two approaches to this. A two-dimensional approach, you look for moments and axes and sums of forces. Okay, so what you're doing, you're kind of looking at the three-dimensional object from different directions and turning it into a series of two-dimensional objects. With the vector approach, you're writing full vector, moment, and sum of forces equations. The 2D approach can be a lot quicker. The vector approach does seem to take a bit more time. Now keep in mind, if I do give you a 3D problem on this midterm, it can't be a full-blown 3D problem like what we did. I think it was on number 283. It can't be that thorough because it would just take you so much time that I just couldn't do that on a midterm. So just be aware of that when you're taking the test and realize that if you see a 3D problem, it might be somewhat modified to make it so it works on an exam, okay? So it might look a little different than what you're used to, say, on that problem. I think, again, I think it was 283. Why don't I give that a quick check, but I'm pretty sure that was the problem. That was the full 3D. Yeah, it was 283. So it might be something that looks a little different than something like 283. Okay, then we have truss method of joints, where you find reactions first, find the angles for the members, and then write up some of fx and some of fy equations for each of the joints and work your way through the truss. And zero force members, I have the sketches down there below of the common situations where you find zero force members. The way you prove that something is zero force is you look at one particular joint and prove that some of fx, some of fy, or perhaps some of fx prime or some of fy prime are zero. It's quite often apparent at one joint for a member, but not apparent on the other joint. So remember, all you have to do is focus on one joint, and if you can prove a member is zero at that one joint, it is zero. Okay, you don't have to prove it out at both joints, just one. Method of sections, find the reactions first, make a cut through the members. The members cut become forces, and then use your basic static equations to solve for the forces in the member. So that's just a quick run through what will be on the test on Monday. I also have some exam problems, or example problems, I should say, from old exams that are uploaded. We'll go over those probably on Friday. All right, let's just take a look at one truss problem. Let's just be sure that that you can work through one of these. So how about having a look at, I think it's 291. It's on page 17A, I think. The answers for it are on page 17, and the truss itself is on 17A. So why don't you start by finding the reactions at A and D, and also by finding the angles of the members. So find the angles of the members and find the reactions at A and D. Once you pause the recording, then I can come back and show you what those are. All right, so hopefully you found the reactions and the forces, and the angles then. So let's have a look. There we go. So there are the angles. So we've got AC and DC have a rise of 2 and a run of 4. So arctan of 2 over 4 is 26.6 degrees. Then BC has a rise of 2 and a run of 1. So that'll get you 63.4 degrees. Okay, now the reactions there, you just take some moments about A, you get the 16,000 Newton force, which is 3 meters away, clockwise, so it's negative, plus 8 RD. And so for RD, it's 6,000. Some of FY will get you RA, it's 10,000. All right, now the next thing you want to do then is just start to work your way through the joints on the truss. To do that, you draw a free body diagram of a particular joint. You want to work on joints where you know a force and you have only 2 unknowns. So only work on joints, generally speaking, where you have 2 unknowns and a known force. So you can start working your way through those joints. Why don't you do that and figure those out? The answers are on page 17. You can check, and I'll run through it too here. But you could work through that, pause the recording and work through it, then we'll come back and go through it. This is just serving as a review for trusses. All right, let's have a look at the solution. So I started at joint A. So what I've got is the reaction at A is 10,000. I've got the unknowns then, AC at the 26.6 degree angle down left, and AB is horizontal. I'm assuming that AC is down left, and then I'm assuming that AB is to the right. Now I'm doing that kind of intentionally. What's going on here is I'm seeing that 10,000 reaction, which is going up. Now the only Y force is AC, so that has to come down to counteract the 10,000. When it comes down, it also goes to the left because of the orientation of AC there at that angle. So if it's going to the left, then AB pulls to the right. I mean, that's what's going through my mind when I draw those arrows in there. Now, if I didn't draw them in the correct direction, that's not a problem. I'll just get a negative answer. So it's not a big deal, but I'm pretty confident that that's the way they actually act. So what I'll do there, I'll go sum of Fy is 0, 10,000 up, minus sine 26.6 times the unknown FAC down. Solve for FAC, I get a positive 22361. Positive meaning it does indeed act down in compression. Sum of Fx is 0. I've got negative cosine 26.6 times 22361. That's the force in AC. That acts to the left, so it's a negative, plus FAB to the right. FAB is 20,000 tension. All right, so now I know AC and AB, so I can start moving my way through the truss now. All right, the next place I go here is to B. What I'm going to do then is I know I've got that free body diagram drawn for B. Now notice what I did with AB. I know that at A it pulls to the right, so at B it'll pull also, and that'll be to the left. It's like a rubber band that you've pulled between your two hands. It pulls both of your hands inward. So that's what that AB, which is in tension, is doing. It's pulling A to the right, it's pulling B to the left. It's in tension. Okay, so I've got 20,000 going that way. I've got 16,000 at B going down, and then I've got the unknowns, BC and BD. So sum of Fy will be 0. That'll be the minus 16,000 plus sine 63.4 times FBC. So FBC is 17,889 upwards, so that's tension. And the sum of Fx is 0. I got minus 20,000 plus cosine 63.4 times 17,889, which I just solved for BC. Those are the two known x forces. And then I've got the unknown plus FBD. Solve for that. It's 12,000 tension. Okay. So that gets me the forces then in BC and BD. And then I can go to joint D and solve for the last one, which is CD. I'll just use sum of Fy to do that. So I got 6,000 up for the reaction. And then I've got FCD coming down at 26.6 degrees. So 6,000 minus sine 26.6 times FCD. Solve for FCD, and it's 13,417. It's in the direction assumed, down right, so it's pushing on D, so it's in compression. Then I just ran sum of Fx also as a check, and I got FCD again at 13,417 compression. All right, so there's an example of a simple truss, and working through that with method of joints. Now, I'm sure that'll be on the exam somewhere, so you do want to work through some of these and get confident and be sure that you can work your way through a truss, okay?